Welcome again. This is the second part of week 10. As I already mentioned, it is a sort of longish week. The two videos will go over the allotted time, but I think it is all material that should stay together because it belongs to one very particular chapter of our course. The goal of the previous lecture was to get a sense of how much advantage one could get by creating into a processor exactly and only those functionalities that corresponds to the minimal programmability that we need in some applications. We have seen these DSPs, digital signal processors, which traditionally tend to do most of these convolution operations, and we have seen how relatively few components, relatively and highly specialized components, tend to be sufficient for achieving performance and parallelism that are even harder to achieve on a advanced superscalar processor. What we want to look at today is all these irregularities, all these peculiarities that we have introduced in the processor, how much they damage our ability to compile for these architectures. It will also give maybe a little bit of a sense of how people can use some of the strange components that are in the DSPs, like these address generation units. But essentially it's more to get a sense of how architecture and compiler interact. So you remember last week we have seen the DSPs, and we have sort of defined empirically through a number of features that distinguish them. The fact that they tend to have these multiply accumulate instructions, the fact that somehow these instructions are arranged in a way where the registers are in between the functional units or inside the functional units, and somehow are special registers that are seldom completely and directly accessible, but somehow meant to organize some sort of software pipelines. We have seen these multiple memory ports with special units that we have called address generation units that are just there to supply and compute addresses for the memory accesses. So supply the addresses and in parallel compute the next addresses for the memory accesses, and these special instructions to execute a number of times the body of a loop, a static number of times, typically a constant, with zero overhead, without paying for the control flow decision. I remind you once more of what they represent, right? If you look at what each of these instructions and these features do, they do some sort of cheap dedicated parallelism, right? The multiply accumulate that have pipelining registers in between are doing nothing else than what we used to do in VLIWs through software pipelining, which is a form of parallelism, right? Of finding how to make in parallel two operations that are intrinsically dependent. Multiple memories, of course, is a form of parallelism. Multiple address generation units is also a form of parallelism, because while I am doing my main computation on the multiply accumulate unit,
I'm using the address generators to do some small computations and trivial maybe computation, sometimes actually not that trivial in terms at least of number of RISC instructions that I will need, but they do some calculation in very specialized calculation in parallel that goes from incrementing a register, decrementing a register, or doing more complex things like remapping the bits, inverting the bits, doing modulo operations for circular buffers. So, and maybe the last one, when we do these zero overhead loops, so we are computing the number of iterations and so on, and we do this in parallel once more to the fact that my main operation in this cycle is multiply accumulate, but there is yet another adder or subtractor that is incrementing some index to figure out whether we are done or not. So it is parallelism. It is the same thing that we do in maybe in a VLIW by having multiple units at the same time, but these units are not in a homogeneous pool with an homogeneous number of registers all in my register file. They are a bit all over the place, and the units are there where it needs, dedicated for a purpose. And so we want to understand what the difficulty will be to use this architecture. Just as a matter of curiosity, until still a couple of decades ago, C code was a minor component in DSPs and microcontrollers. A lot of the programming was still done in assembler. I don't have a similar information as of today, but I would expect this to have changed dramatically today. I would expect that most of the code, at least in number of lines or in number of instructions in my code, is from C code, and whereas in microcontrollers probably there is almost no assembler left, except for maybe those instructions that are not representable in C code, exactly like in our typically, even in my x86, right, whatever is some management of peripherals doesn't have a correspondent, needs to be in line basically in C code, so it's assembler anyway. Whereas this happens in microcontrollers, what I expect is on DSPs there are important parts of code that are still written in assembler, but they are just the very critical loop, and most of the code, which is probably in number of instructions, the majority is now written in C. And maybe some of the critical code also manages to be compiled reasonably from C code without resorting to assembler. So what we are looking at today, again, is a sort of the old version, because we are taking this more as a sort of pedagogical exercise, right? Trying to understand what goes wrong if I do the DSPs as I was doing them 20 years ago. What prevents me from compiling well? For this, I think we need to be clear about how compiler work. I mean, not in the very detail, this is not a course on compilers, but we need to understand a few of the basic operation that a compiler has to do. I don't know, and I cannot ask because of the situation, and we are not in person, I cannot ask you how much experience you have with compilers in general, but this is a representation of a typical compiler that is usually split in two parts. One front-end part that is essentially what is independent from the target machine, from the target assembly code to produce, and depends completely, so to speak, from the language of the source code. And then there is some IR, some intermediate representation that in the ideal case is one representation that is used all over the compiler from this moment on. And this from this moment on, we enter in what people call the back end, which is the dual opposite of what we have seen before, in the sense that there is no dependence anymore at this point from the source language, whether it was C, Fortran, or Scala, or Java. Well, these are a little bit different languages, maybe, because they don't compile into assembly, but Fortran and C maybe are good examples. And on the other hand, it's increasingly dominated, all this part of the backend, by the target machine, by the fact that we need to produce assembly code for a given, very specific machine. Whatever we are doing here is concerned about the second part, right? The first part is more high-level optimizations, analysis that maybe is used by the second part, but is done on the source code, where typically I have more visibility about the programmer intent. I have information about types and so on and so forth, right? Or on array sizes and so on and so forth. And this tends to basically usually disappear while I go through the back end. So what we want to do is to review very briefly again, because I don't know how much you are comfortable with this part. What I want to do is to review a little bit this part, the part that people call code generation, essentially the different parts and phases that one has to go through to generate assembly code, which are essentially three: code selection, instruction scheduling, and register allocation, often in this order, but not always. You probably happen to know that compilers are not as simple as the figure suggests, that the dashed border here between front end, back end is absolutely not as clear as it should be, and that there is a lot of information that sometimes needs to be passed across this border to do the proper thing. But we'll see the sort of simple view that is typical of a compiler course here. So we say these three techniques, and what are they? Code selection corresponds to selecting the instructions that we want to use for a specific computation. So the keyword here, the key starting point, is the DFG, the data flow graph. I'm reasonably sure that is clear to everybody what it is. It's the kind of figures that we have seen also last week, that we used with all the operations and all the dependencies between these operations. And these operations are the intermediate representation operations, so they are just an add or a multiply or a load or a store. But then there is still a question of what is, among the different adds, the one that we want to use. Why different adds? Because there are adds that take maybe the two operands from the register file. Maybe in my architecture there is an add that takes one of the operands from memory, or there is an add maybe even that takes two operands from memory. So in this case, it's not a priori completely clear which add we want to choose. The second problem is instruction scheduling. We know very much about scheduling because it has been one of the big topics of the first part of this course. But so the problem is when to place an instruction in the executable. For VLIWs, we have seen is much more than that. Is exactly when they will be executed at runtime in dynamically scheduled processor, since there will be yet another scheduling that will happen later in hardware, is actually when they will be fetched and therefore considered for execution. And the last one is register allocation. We have, if you think of a data flow graph, we know that this addition depends on two previous, I don't know, a multiplication and a division. So I know where my operands come from. What is not said in a DFG is where this value has to be stored. Do I need to store it? Can I store it in a register, in two registers, because I have two registers available? If I don't have any more registers available because I have too many results on my hands at a given point in time, shall I spill to memory, as people say? That is, shall I save it in some location on the stack and take it back later? And which value should be spilled is more convenient to spill. So I'm going to review the classic techniques for these three problems so that we'll also understand a little bit more the three problems, because somehow we'll look at some of these problems also in the context of some DSP architecture. So the first is the code selection problem. If you know something of VLSI, is actually almost identical to the problem that is called technology mapping. So you have an abstract representation of the computation that you need to do, and what you have is that you have a set of possible subgraphs that you can map, that you can use to cover the DFG. So the point is that you want to cover the DFG, you want to have every node of the DFG associated with one of these instruction sets, and you want to have this with a minimal cost. And each of these elements that you can use to cover this instruction set has a cost. You can, if it helps some of the people, maybe more electrical engineers that know a little bit more of VLSI, you can imagine exactly the same problem in logic synthesis, where you have here a logic network. These may be ANDs and ORs and something like this, and XORs, inverters, and so on. And then you have here your standard cell library, and what you want to do is to find a way to use standard cells to cover your circuit. It is almost exactly the same problem. I want to remark here, and I'll try to make this remark in all these three little chapter reminders, that this is a problem that has been trivialized to a large extent, at least, by the RISC architectures. I think I mentioned it a few times that in the ISA architecture of x86, you have a variety, for instance, of addressing modes, right? You have an add, but the add is not necessarily an instruction that comes from registers. I was actually also saying it a few seconds ago without meaning it necessarily for the x86. But then sometimes maybe I add and one of the operands come from memory, and maybe from memory with a specific address calculation, and between with, I don't know, an addition between two registers, a base register and an offset register, and something like this. So in that case, is instructions a bit like this, not exactly this one, but where you have here a load, and here you have a memory access, and the memory access has a calculation. And this is a complex instruction where there is quite a bit of potential of choice. And why has it been trivialized by RISC processors? It has been trivialized because there is only one add instruction. It is between two registers and produces a register. And that's the only possibility. Okay, there is also the one with a constant, but they are two very different cases, because in one case here there is a variable, in the other cases there is a constant, which is a very clearly different situation. So given the fact that I have here two values that are non-constants, there is no choice. So when there is no choice, the code selection problem becomes essentially trivial. And the good side of this is that my compiler, it cannot do a wrong choice if you want, right? Because there is no choice. So whatever I do, it's the correct thing that I'm supposed to do. When you don't have a simple situation like in risks, the way to do this is to break the DFG in trees. What does it mean in trees? This is already a tree, for instance, this DFG. What makes it not a tree? What makes it not a tree is fan out, is the fact that this result will be used somewhere else. What maybe in compiler is also called a common sub-expression. A sub-expression like this that is used here, but is used, imagine, also somewhere else. And in this case, this is not a tree, so what you will do is to cut this into trees. So whenever you have some reuse of a variable in different computations, you will have a forest, a set of trees, and for each trees, you will use a tree grammar. Essentially, you define all the instructions as this one. For if I need to do an add and I need to produce a register, I can do it from any two registers and it has a cost 1. And you try to cover, you basically have very good algorithms that are actually optimal and take only on time, by which you go through this tree a couple of times and you have the optimal solution, the minimal cost solution. Now, this is, and it will become very important later, and we'll discuss later maybe why it is not so important for RISC processors. This is true for trees, data flow trees, not for general graphs. So I need to break it up. I have data flow trees, I can do an optimal job very efficiently. This is code selection. This is an example maybe, and this is an example of choices that you may have, or two solutions that are equivalent, where I'm using the Mac in two different sides of the operation. There are two different clusterings that are, in this case, equivalent. And again, here there is no big sort of choice or difficult decisions, but the point is that the Mac costs 2 and the mole costs 2. So if I do these two together or these two together, I save 1 cycle or 1 unit of cost, or whatever it is. I suppose it's the number of cycles to not to do or to incorporate this addition in one of the two multiplications here, which is represented. The second problem that we care about is the scheduling problem, right? The idea is that we have a sequence of instructions that correspond to a schedule. If I know what is the rule of instruction of the different the rule of execution of the different instructions and their latencies, and because of these latencies, I need to respect all the dependencies. We know these things very well, right? Because we have done enough of this, and we can do this. We need to respect the available dependencies. I cannot, the available resources, I cannot schedule on the same cycle 3 additions if I have only 2 adders. So it turns out that this is an NP-hard optimization if I want to minimize the schedule. And so typically you cannot find an exact solution. The way typically one solves this problem in compilers is a simple, greedy heuristic algorithm that is called list scheduling. The point is that one maintains a ready list that contains all the instructions at a given point in time have not been scheduled yet and could be scheduled in terms of dependencies and resource availability, and pick at every step one instruction from this ready list. And we'll use a priority function to decide which one is the most interesting instruction to start next. So the idea is to pick, I don't know, something like the instructions that have longest latencies or longest potential latencies, like a load word or a store word. Sorry, not store word, I'm sorry. A load word because it may be a miss and it will take hundreds of cycles, so let's do it as early as possible. Or maybe you do some analysis on critical path, critical execution path in terms of number of cycles, and you try to execute those instructions that are on the critical path, or something like this, right? So one of the great things is that it is a pretty simple heuristic to put in place. It is very easy to understand this heuristic, which I think is usually a very good predictor of the success of a heuristic, right? The heuristics that you can understand are often more powerful in the applications than heuristics that are a bit, say, mysterious, so to speak, or too articulated. And that's it, essentially. It's interesting also maybe to compare this with what we have done in hardware inside the processor. And you could say that the ready list is a subset of the content of the reservation stations, right? When you go in the reservation station and look for ready schedulable instructions, you're doing essentially this, and you're doing it in parallel for all the functional units. What we have said, I think, when we were discussing reservation station is that maybe the priority function is simply a random function. Let's pick one that I find. Maybe in implementation one could do a little bit better, and then it would be even closer to a classic list scheduling implementation, but an implementation in hardware. The third of the problem that typically is faced by a compiler is to decide where to place the different values, the different intermediate values in the computation, and specifically in which registers to put it. Typically, the internal representation of the compiler has some form of virtual registers. Typically, virtual registers are one single use register, so every time that I have a new value, it gets a new virtual register, irrespective of the limitedness of the number of registers in my architecture. We don't take that into account at all. I have an infinite number of virtual registers that maybe they never get reused, maybe sometimes get reused, but basically don't have the constraint of the physical registers. And the way people proceed is typically by looking at the liveness of the values that are in the registers. So that is, when there is a value during the execution of code, there is a value in a register that is of interest. I think it's best explained maybe with an example. Maybe if we look at this code and I look at VR0, VR0 is clearly alive here in the sense that since I'm reading it in this piece of code, I don't know where it comes from, but there is something valuable in 0. And VR0 is still read here. So again, there is something valuable in 0, in virtual register 0, here, here, and here. I also notice here that I'm writing in VR0 some new value. So from the next instruction, there is certainly something valuable in register 0. But that also means that the value that was in virtual register 0 here is dead, because nobody can read it anymore, right? The moment it will be overwritten here, there will be a new value, and here there is no value that I care for in register 0, right? Similarly here, for instance, you see also with 0 is that clearly this is the last reading of that value that is in VR0, because here I overwrite it with yet another value. So here there will be yet another live value in 0, but in these two instructions, during these two instructions, there is absolutely nothing of interest in VR0. So if one does all this analysis, and you can maybe double check some other register in this example in here, what people do use as an approach is to create a conflict or an interference graph, where I say, so which other value is present in the machine or is useful in the machine at the same time as a value is in VR0. So let me say it again. I have here some value in register 0, and at the same time there is a value in VR1. And at the same time, by a similar analysis, there is a value useful in VR4. So I go here and I say 0 and 1 cannot be allocated. VR0 and VR1 contain two values that cannot be allocated to the same, sorry, it was 0 and 4, right? 0, 1, and 4. So 0 and 1 and 0 and 4 cannot be allocated to the same physical register because I need these two values at the same time, right? And if I go back again 1, there is here 0, 1, and 3. So it's not only 0, 1, but 0 and 3. And therefore, I have also a conflict or an interference edge between 0 and 3. That is, 0 and 3 cannot go in the same register. Once I have built this graph for all my values, for all my virtual registers, the question is to color it with at most K colors. And what these colors represent, so they represent my physical registers, right? For instance, here on coloring, or the optimal coloring, says use the same color for 0, 2, and 5, because there is no edge that links them, which means that they are never containing the virtual register 0, virtual register 2, and virtual register 5, never contain at the same time something meaningful, and therefore the same physical register is good for them. So if I go back and I look here, register 2 contains something useful only here. Register 5, sorry, let me remember, register 5 contains something useful only between these two instructions, right? Between two instructions, and register 0 contains a lot of actually useful stuff most of the time, but never at the same time. 2 is here and there is no 0. 5 is here and there is no 0, nor 2. So I can take whatever is called VR0 here, VR2 here, and VR5 here, and all put into a register, whichever, it doesn't matter which one, R3, physical register 3. Right. This is the idea. I'm doing graph coloring. That is one of the classic NP-complete problems. So it's a hard problem to do. It's actually much more complex than this, but we are not going to move there because actually the question is not that I want to color with a minimum number of colors, but actually I want to use at most K colors. So I need to do something like spilling, decide on which one of these I give up and I put in memory. So it's a bit more complicated even than that. But there are very good heuristics for doing this, and it's something that in a sense is given for solved and the compilers can tackle very well. Now, I want to emphasize two things on what we have done, we have seen here, which is just a reminder of some extremely basic compiler cores, backend compiler, optimized compiler cores. One is the user of heuristic is almost universal. You have seen that even when we claim to have an optimal solution, the optimal solution is for a partial part, a partial problem with respect to general problem that we have. And in this decomposition of the large problem, remember the forest, the decomposing the data flow graph in a forest of trees, I have an optimal solution for the trees, but I need to do this decomposition, and this decomposition is in some sense a heuristic, because the optimal global solution will not be found. One other consideration is that these phases are essentially considered mutually independent. That is, there is no influence of one phase to the next. One of the things that will come back later, but we can say already here, is that, for instance, in a RISC processor, it's done in such a way that I can put here and here absolutely any of my register, or at least any of my general purpose registers. And my general purpose registers are all essentially equivalent. Why that? Because I want to do this job in a simple way. This will tell me put 0 and 2 in the same register. I'll decide one of my registers at sort of random because they are the same. So I say physical register R1, and I will want to put here R1, here R1, here R1, and so on and so forth. Now, what I don't want to be is to be limited here in saying, oh yes, but you can put only R1 or 2 here, and here you can put only R3 and R4. And so, for instance, I'm screwed because I cannot put the same register in these two positions. Which is, again, one difference that I like to emphasize since we are here, between RISCs and CISCs. If you know something of the x86 instruction set, it turns out that basically you have most of the operation have as only possible destination and one of the two source registers, a register that is called AX, or which the A stands somehow for accumulator. It's one of the registers that in the original x86 architecture at the very beginning was a very special register that most of the instructions could address, and many of these instructions could not address any other register than that one. So it was a very peculiar register, and in many cases, instruction selection and register allocation were linked, because the moment I choose one specific instruction, automatically I know that I need to use AX. And this will create a lot of problem, because this, in a sense, naive or simple or straightforward approach to register allocation will simply not work. And I will have some link between maybe I can choose another instruction here where I can put any register here, but then I have something else. It's a different instruction. Maybe I have another instruction that results in the same, gets the same result, but I can only use AX, but has some other advantages in terms of the operands that I can bring in. And you will have this link between the two phases. And one of the things that RISC did is forget about this, right? I have an add, I can put any register there. I take any two registers, and I produce any register as the destination. And finished. And this made, yet again, for the RISC extremely easy to create good compilers. And while x86 was struggling to create similarly good compilers and develop good heuristic for them, RISCs were sort of taking off. And what happened, if you look at the instruction set of today, is that, in fact, these instructions that are lopsided, that have some registers as the only possibility, still somehow exist somewhere in the manual, but are obsolete and not recommended as a target for a compiler. But you have, in addition, instructions that are perfectly RISC-like and symmetric. So one of the things that you may notice if you look at the instruction set is that we say x86, almost assuming that is the same instruction set since 30 or whatever, 40 years, but in fact is an evolving instruction set where some of the legacy has been left there, executable if you really want, but a complete sort of new instruction set has been added so that you can do what you want to do with modern architecture and create great compilers. And that part of the instruction set is the target of your compilers and is actually the part that is executed very efficiently, and the rest is there for compatibility. It is there, so it is still compatible, but it's not what gives necessarily the performance. So what RISC tried to do, to come back to this slide, is decouple the problems. Because these problems are intrinsically very hard, they are all NP hard, NP complete, or worse. The idea is to make the architecture in such a way that if I don't consider selection, code selection, the moment I do register allocation, or maybe rather vice versa, I don't consider the problems that I will have in register allocation the moment I'm doing code selection, I will not lose much because I will do an optimal maybe or a good choice for the code selection, and then register allocation can be done anyway, so no big deal, right? So this was one of the big achievements of RISC instruction sets to help independency of these three phases that we have seen. Okay, so now that we have seen this, let's see some of the problems that DSP bring, in a sense, back, right? Life is easy in a RISC-like environment where we have a compiler like this that operates. Now, what happens with DSPs? And we're going through 3, 4, I think, problems, maybe some relatively quickly, and I let you, if you are interested, read the papers that are on the web about the details. But to get a sense of how they break some of these considerations. One set of problems, or the first two problems that we are going to look at, are connected to these address generation units. I hope you remember from last week what they are. They are these places where you have an address register pointer, basically a part of the instruction register, a part of the encoding of the instruction, if you want, that says to address through one register AR0, and they send AR0 to the memory. So you are making essentially a load or a store as part of a more complex instruction. In other words, you are fetching some data directly from memory for a specific computational instruction. On top of that, and what is the characteristic of this is that, I mean, this will be absolutely normal in any architecture, right? You have any indirect operator through memory, but the specialty that you have here is that you have maybe a lot of fairly complex computation. Complex maybe is not the right word, it's sort of still trivial because it's auto-increment, auto-decrement, but still some very peculiar computation of the next value of the same register that you read. So this picture is only an example of what one of these address generation units, actually a relatively simple one, might do, but gives us the sense, right? I have several registers and I can post-increment, post-decrement of different values that are either constants or are values that are saved before in some modifier registers that exist in the same address generation. So one of the questions is, how do I use them well? And especially, how do I use them well when coming from arbitrary code written in suppose C, C++. And we look at two of these situations where we want to make use of them. One is a case where, to use them better, we want to change the way words are stored in memory. And I'll come to this a little bit in a minute. And the other one is where I cannot change the order of variables in memory, typically because they are part of a vector, of an array. So the array is fixed. There is element 0, then element 1, then element 2. So I cannot change the order of the elements. So when I have something fixed, how can I use the address registers to access well the values as I need to access them? Both will become, I guess, much more clear in a moment. And maybe let's forget for a second the formalization. I think it's much easier to look at a specific example. So suppose that you have an architecture where you can only increase and decrease an address register, and you have only one address register. Okay, so I have one address register. I can easily auto-increment, auto-decrement. I have 4 variables that I have to store somewhere in memory. And my program has, for whatever reason and for whatever purpose, accesses these 4 variables in this sequence, right? Accesses B, then accesses D, then A, then C, then D, then A again, and so on and so forth. What is the problem? The problem is that if I have declared my variables A, B, C, D, one after the other, typically my compiler puts at some address, it doesn't matter if it is 0 or something else, probably not 0, but somewhere places the variable A, then I declare B, then it puts B, I declare C, then it puts C, and then I declare D, and it puts D. If that is the case, if I do this and I look at how I will be accessing these values in my code for a processor that doesn't have a normal load store unit, but can only go through this address generation unit, what will happen is that I will have here, for instance, an access to B. I need to load AR with the value 1, right? Because I don't know what the value is because we haven't started, so I need to initialize it to 1, and I need to do the access. So I have to pay some price of loading the address register. Then if the next access is to D, D is 2 addresses or 2 incrementations farther, right? And my address register can be implicitly only auto-increment by 1 or auto-decrement by 1. So I could go and reach C in an auto-incrementation, but I cannot reach D, which means that I need to modify manually, maybe reload IR with the value 3 before I can access D. And again, there is this asterisk to say that I need to pay a reloading of AR price to access. Of course, it's not always the same case. For instance, if I am here, so let's make a jump here, if I just access C, and for accessing maybe I paid, it doesn't matter, but I just accessed C, if the next access is to D, I could have just auto-increment the address register that I had before, and the access to D is for free, in the sense that there is no loading of the address register, and so I don't pay the price. So I think you understand the idea, right? What I'm measuring is that I'm measuring how many times here I have to reload AR with a new value because I'm not addressing one of the adjacent values of the previous one, and how many times I am in this favorable situation where I can reuse and I don't have to reload and to pay any price. And here the cost is 9. There are 9 times, if you go through this example, there are 9 times that in fact, it's very easy to also count, right? These are not adjacent letters. So it's 1, not adjacent 1, not adjacent 1, not adjacent, sorry. So 0, 1, and so on and so forth, right? Okay, so this is the situation. What I would like to do with my compiler is that since I don't care where these variables are in memory, because they can be at any location, I couldn't care less, right? I would like to find out if there is a different ordering, like C at address 0, A at address 1, D at address B, 2, and B at address 3, where if I go through exactly the same sequence, because the sequence, again, is fixed and is typical of my program, I have less occasions where I have to reload the address register. So I always have to load it on the first one, but now I do B to D. B to D are adjacent. Then from D I need to go to A, they are again adjacent. From A to C, they are adjacent. Now I need to do D, they are not adjacent because I have a distance 2, so I need to do a reloading. And you see here the situation, if I do, for instance, this sequence in memory, this memory layout, I have only 5 reloading, so I gained maybe 4 cycles or 4 instructions. Okay, so this is one of the ways people try to use these address generation units when they write manually code, and now you would like to do this also as a compiler optimization. Now, it's not a terribly difficult problem, at least in the simplest formulation, right? If I have exactly the problem that I'm saying here, where I have a single address register, AR, and I can only auto-increment and auto-decrement, what I could do is to capture into a call it an access graph, maybe, where the nodes are my 4 variables, how many times I'm going to access B after A or A after B, right? So if I'm doing this access successive between A and B, how many times? So if you go back to our sequence, how many times A and B are successive? A, no B, A, no B, A and B are one after the other, so once, no A and B, no A and B, finished, only one, which is the value that I find here. If I look, for instance, between A and D, how many times they are neighboring access? Once, twice, 3 times, and 4 times, and so I have these 4. And when I have this access graph, it's relatively simple to formulate what is the maximization problem that I want, because what I want to find is a path, an Hamiltonian path, that is a path that goes through all of them, which will represent the linear sequence of the values in memory. And I want this path to have maximum weight. That is, I want to save, because these are the number of times that I will save reloading the address register. So I want a path that has the maximum weight, right? So the path will be the sequence BDAC or CADB, which is equivalent in memory, and the maximum will represent how much I save. Now, this is an easy problem because there are great heuristics, right? You can have essentially a grid heuristic where you say, okay, let's try to get the maximum amount that I can save first. So A and D will be absolutely neighboring. Then let's see what is the next one that I could gain most is 3. So definitely C and A will be neighboring. Then, well, I would like to have these 2 neighboring, but it's not a path anymore because I already visited D, so I cannot visit D again. So it's not a valid solution, so I don't do this. So the next, and actually only one thing, not the one thing that I can do, but one of the things that I could do is to add this to have a path, right? In this case, for instance, very clearly the this Hamiltonian path is actually optimal even in the greedy formulation. Now, the problem with these things is that, yes, and this is true, but this is true only for one address register, but actually I have many, right? Maybe I have 4 in my example before. So I could start to essentially do some extension to this algorithm by saying, okay, let's sort of partition basically the different variables to different ARs. I use AR0 to access some of them, and maybe A and D, and I use address register 1 to access B, C, F, and D. How do I decide this? By doing the same access graph, and by trying to have some sort of similar greedy algorithm. It's not actually exactly as intuitive as it may be, but I try to do something of that sort. Again, we are far away from what you really want to do, because now I have multiple address registers, but I've also an auto-increment and auto-decrement range that can be more than 1, right? So far, I can only auto-increment by 1 and remove and subtract 1, but I can have, as we saw before in the image, maybe 2, 3, or a different constant. I have also the flexibility to load in the modify register some values, right? There's some values that occur many times and are not constant that I can use. I could put there. So you can easily imagine that this started with a problem that is incredibly elegant and simple, and become a mess that is even writing what are the coordinates, the formal definition of the problem becomes extremely hard. And so people do what they do in this case, go with meta heuristics like genetic algorithms, or you will see later in some other case, people use simulated annealing, which are maybe sometimes very powerful heuristic, but are somehow the heuristics of who doesn't master anymore the problem, right? If you master the problem, you have an elegant, simple heuristic like the one we have seen before. If you can't, you go for these things. And these things cost, right? For instance, you see the runtime to get, per chance, I suppose, the optimal solution here in the problem with all the coordinates of probably a commercial processor of the time and on some benchmark, you have to spend of the order of some seconds to get only this problem solved, which is a very minimal problem in the compilation. So if you imagine that you are usually annoyed when you are running GCC that takes too long to compile your program, now imagine that you have several orders, some of the components that are several orders of magnitude longer, right? So it's one problem. Another problem that is linked to the AGU, so that was our first problem in compilation, right? Where if you want to use well these AGUs, you need to spend a lot of time for, in reality, somehow relatively little problems. And here is another one, again linked to the AGUs that I anticipated before, is when you want to have these AGUs to access memory typically in the form of arrays. And since they are into arrays, you cannot control the position of the elements like we were doing before between these ABCDs that are 4 variables that I can put wherever I want in memory. Here they are fixed somewhere. And actually, I probably have a loop where I am accessing different items like this. Except that people don't write, when they write C, and they still call it C, but I object that maybe it's not really C in the spirit of the language. They don't write this kind of expressions as the loops where there are these affine computations, but actually write something like this, which I hope you'll agree with me is totally unreadable. You see that PA is essentially a pointer that moves inside array A, PB moves inside array B, and so on and so forth. And here, what I do is that I have PA that is auto-incremented, left alone, auto-decremented, and so on in the code. So essentially, this is the same code that you might want to write this way, but has been rewritten by having explicitly some pointers that get auto-incremented and auto-decremented to do the same thing. Why one will do something like this? Certainly not someone in a good mind, because this is readable or nice code, right? This is horrible. But it has one advantage. It tells almost explicitly, right? It's not explicit, but it's done on purpose to have the compiler say, oh, it's great to allocate an address register to this, an address register to this, an address register to this, and yet another address register here, and then auto-increment these address registers when these operations get performed. So essentially it says to the compiler, do this job for me. I'm telling you how the solution, how to do things well. And what we would like to understand is why compilers don't do this themselves. Why do I have to solve the job for the compiler? And the problem is that it is pretty complex, right? The situation that we want to have is that we have a sequence of accesses. In this case, for simplicity, they are all to the same array. It's again a sequence that is given, and the question is, how shall I allocate the address registers so that every access is done without reloading any of the address registers? So essentially, we want to partition these accesses among or across the different address registers using a minimal number of these address registers, so ideally one, but in general it will not be possible, so that they every next access is computed with auto-increment. So again, here, if we have the example of a single address register and, a single array and a pure auto-increment and auto-decrement, the idea is to have these nodes that correspond to my successive accesses and have edges between the two of them when they can be performed with auto-increment and auto-decrement. For instance, if I am accessing I plus 1, I can access in the next cycle I by auto-decrement, or I can also access I plus 2 with auto-increment. But if I just accessed I can access I plus 2 because I've only auto-increment and I should increment by 2, so this I cannot do. Here I need to decrement by 3, so I cannot do it, but if I accessed I plus 2, I can access I plus 1 by decrementing. You see the idea. So there is an edge for everything that can be done, for any sequence that can be done by the address register with auto-increment and auto-decrement, and therefore the idea is to find the minimum number of paths that cover completely this graph. So in this case, you see the solution here. I cannot do everything with a single path, so I have this path to cover these 4 and another path to cover the other three, to link the other three. And what each path represents is one address register, right? One address register that will do these 4 accesses, and the other address register that will be used for the other accesses. Again, this is much simpler than what reality is. The first thing that happens is that you want typically that whenever you have a situation like this kind of accesses, most likely they are part of the accesses that happen inside a loop, right? This is the body of the loop where you have this sequence, then you increment I, and you do the same thing again. Right? And so if you want to represent this, you need to also have nodes for the next iteration, which is here. And then you need to see where you can go to the next one, taking into account that I will be either incremented or decremented between the two. So what we will want to have is a path, but not only a path that visits the maximum number of elements in yellow, but also that ends always in the same, in the corresponding node where it started. So that is essentially ready for the next iteration, right? So it must be possible to go from here to here, which is because this is I+1 and this is I+1 where I has been incremented. So it's in some sense I+2, and it's just an auto increment. So it's absolutely possible. So, okay, again, we can do, except that now it's a bit more complicated than the problem that we had here. And if here there was an ON algorithm that maybe is not optimal, but is very efficient, now we don't have this anymore, and you have only very shaky heuristics. And you see also here the problem now. This is only for one set of it, for accesses with one register. You may have one array, you may have a multiple array. So again, things become very quickly more complicated. In practice, people, I think mostly still today, write code like this so that the compiler knows what to do, and it's very hard to solve the problem elegantly. Good. So we now move to the third problem in a completely different area of our DSP processor that we want to address. And this is how to use these special functional units that may have some special registers that are essentially special purpose registers meant for some specific use, like in this case, to a human, it's absolutely clear what this is. This is a pipeline register between the multiplier and the ALU. So I suppose that we want to do something that, if you remember the piece of code that we have seen in the last week, I have the multiplier that puts something here every cycle, and I have the ALU that every cycle takes essentially the value of the previous iteration to do an accumulation. So it is a pipeline. So this intent is absolutely clear to us human, but how do we get compilers to take arbitrary code where I do say you need to multiply and add something and you get the perfect use? So what is the simple way to go about this? The classic way, as we said, is to take whenever, so this is maybe the figure that I was alluding and describing before, is if I have a graph that is not a tree because there are common sub-expression, T1 is a tree that computes a common sub-expression that both T3 and T4 uses, what I need to do is to cut here, and treat independently these trees. Now, it's suboptimal for some reason, but actually in most cases it will revert to the same thing in a RISC processor, because you see it represented here by the color of the values at the border between the different regions. If I have a value that I am producing here and this value is used here, I can easily permute my use of the registers in such a way that the register that I use here and I use here for that value is the same. Why can I do this in a normal RISC? Is because all the registers are equal. So whatever solution I found here, I may be able to do this. Now, this is not completely true if you think long enough, because there may be multiple values for the different regions. There may be situations where this doesn't work so well, but basically, this works most of the time and brings you to either an optimal or a quasi-optimal solution. Now, what we may want to do is to essentially do the same thing here, right? At least is the most natural thing to think, is to say, I do a tree and I need to do this for a single tree. I need to do the code selection, I'll do it, the code generation, I'll do it as I do it normally, and then we'll see what happens when I do register allocation. Except that when you are doing the code selection, your rules in your grammar are not going to be generic in terms of registers. For instance, here is an example, is a silly example probably of a processor. If you remember what was on a few slides ago, maybe you don't remember, but you can either go back or simply imagine, we had a rule for add where we said if it is a RISC processor, I can get the add done into any register. So here there would have been written reg without any specification of with reg. And this would result from two registers that again are written like reg without any characterization, because they can be any registers, right? So there is an instruction with what this would have meant, right, with the anonymous registers is whenever I need to do an addition of two values, then it can come from any register. I have this instruction that can do the addition and put the value into any register, right? And this is a perfect description of the add that you all know in MIPS, for instance, right? It takes two registers, produce a third register, and there is absolutely no constraint. Now, if I do have constraint, because now my architecture, like here, can do the addition, but the operand, one of the operand of the addition can come exclusively from one of the registers that are here, the one thing that I can do is to model these constraints in my grammar and say, for instance, here, I have an instruction add, I have only one that can do the operator add, and it takes register 1 and register 2, so no choice, and it puts the result into register 1, so again no choice. So in this architecture, the addition can only be done between these two registers and in exactly this way. Now, I have instructions that can move register 1 somewhere else, and there is an instruction move. There are two forms of the instruction move that can take register 1 and move it in register 2 or move it in register 3. So I have some flexibility, but this flexibility is expressed for what essentially is the same instruction, but by different encoding. So we would so we are basically de-anonymizing the registers, because since they are not equivalent, we have to be explicit of which combinations are possible. Now, if I were to do something like this for the RISC processor, I would have 32 possibilities here, 32 here, and 32 here. So I would have 32 times 32 times 32 rules to express what add can do, and will be crazy, and we will never be able to do. I'm lucky here because this architecture is, on the opposite, extremely constrained. So I have a relatively small number of rules in the grammar, but they are not in this case, which is extremely simple, but there will be probably many more more rules that there will be in a RISC processor, because now I need to replicate each instruction for every possible combination of registers that exist. And again, here the only example that I have is the instruction move that becomes move 2 and move 3, but they are the same instruction, where I do move from register 1 to register 2, from register 1 to register 3. That is, I have to enumerate all the possible combinations. Once I've done this, I can use the absolutely normal tree parsing methodology, which I'm not going to describe in every detail. You can take one of these papers, the paper where this comes, that is mentioned in the references at the end and is on Moodle. But essentially what you do is that you go and traverse the tree from the leaves to the root, and you keep annotating the nodes with all the possibilities that you have available for doing the operations up to that point, right? For instance, if you want to have the value of this mem in register 1, you could do a load and it will cost 1 cycle, or you could bring it to register 2 by doing a load and a move that is spend and therefore spend 2 cycles, one for the load and that brings in register 1, and one for the move that brings from register 1 and register 2. So you have these 3 possibilities here, these 3 possibilities here, and then you go down and you see how you can combine these possibilities, applying all the rules that you have to produce in the 3 possible registers, in the 3 possible locations, the variable, the value, the result here. And then you go down and you go down, and basically you figure out that there are 2 ways to bring it register 1 the value through 2 different instructions, and the total cost to achieve one or to achieve the other is different. So this is the optimal solution, and is the optimal solution that you find here. So all this is nice and good. Again, it's maybe much more complicated because you have many more rules. I repeat once more, right here, there is only one example of where you have to enumerate all the possibilities of the instruction. Luckily, the more constrained is your architecture, the least this happens. But in principle, you have an exponential growth of the rules that you can apply, and therefore of the complexity of getting this optimal solution. But the point is that the problems don't stop here. You have now had to rewrite your problem of code selection to do essentially 2 things: code selection and register allocation. But now you cannot do register allocation anymore, because register allocation, I think it's, hopefully is very clear here, right? It's implicit in this. For instance, the fact that you have used here Mac and you finished in Mac means that your result is in register 1, no choice, right? So what is the problem? The problem is that now you take your independent subtrees for which you manage to apply this with still ON complexity, so something that is still manageable probably despite the exponential number of rules. But what happens to you is that you need to connect. But now you cannot connect anymore as easily as you were doing before, right? You cannot say, let me permute all the registers in T4 so that I can use the blue register for this value. Because this schedule, this code selection inherently takes the value from the green register. And of course, if you say, okay, well, it's just a little inefficiency because what this will mean is that I will have to move, to add one instruction to move from blue to green, and go back and look at this picture, right? Again, it's difficult to use this picture because it's a bit abstract and probably very imprecise, but I hope you can get a sense of the idea. Unless I use PR0 to do this part and this part of the calculation, and PR happens to be the register naturally in between, if I have used a completely different register that is somewhere else, and I have to go there and come back there for doing this copy, well, you understand that it makes no sense at all, right? It's not a little cost that I have to introduce between two threes. I've nullified the sense of this architecture, right? I lost completely the sense of this architecture, and I lost it because I didn't see the instruction selection and register allocation at once for T1 and T4. So this is a big problem, and it's a big problem that actually also implies some part of scheduling, right? If I have a double use here of the same value, I need to figure out how to schedule, right? Shall I do these two operations in sequence, so whatever is this part of code and then this part of code, or shall I do this part of code and this part of code, which has the opportunity of making me accumulate the result of the multiplication in the same instruction? And so in practice, what one ends up to do, if you want to generate a reasonable code for this extremely complicated architecture, extremely highly constrained, is that you end up having the three phases, code selection, register allocation, and partially also scheduling, essentially at the same time. And then the result becomes that is a gazillion of solutions that you need to consider to put everything together. And again, you have to resort to techniques or to optimization techniques that are not only heuristic, but they are meta-heuristic in the sense that you are not describing any, you cannot make a real decision on what you are doing. You just put the thing into your machinery and hope that you get something. And you do get something, of course, because these techniques, if they are well used, function well. Like you see here some results where they do get at least quantitatively closer to what you can hope to do, but you get it for a potentially huge time, right? For just one maybe loop or one small kernel, you're spending 1 or 2 minutes just for the optimization. Before we move on, let's think again, right? What is the source of the problem is that you cannot decouple anymore the different phases. You cannot do instruction scheduling and register allocation separately and hope that somehow when you put the things together, the fact that you did not think of register allocation when you did instruction scheduling somehow doesn't give you a particularly bad result. Now it all depends from making all these decisions at once. Last part, which moves to these more modern architectures, right? This is much more closer to how these days these kind of architectures look, these kind of processors look. Remember, at the end of the previous week, we looked at this TMS processor, TI, Texas Instrument processor. TI has been for a number of years. I'm not sure that they are still, but the market leader of DSPs overall applications or overall application domains. And their key architecture, or many of their processors, were done around this architecture. What we said last week is that this is a fantastic VLIW, fantastic in the sense that it corresponds exactly or quasi exactly to our naive intuition of what a VLIW is or should be, right? The register bank, remember, with all the ports for all the units and all the units that feed back into the register bank. So all I have to do, again, it's not so simple as we know, as we have learned, but is to tell every cycle what the different functional units need to do. Except that, as you see in the figure, that's not the whole story. There is the complete story is also on the other side. There are two clusters, as they are called. So is what is called as a clustered VLIW architecture. Why it is so? Why there is not here a big register bank with all these ports in and out? Well, essentially it is that I think the estimation for the complexity of the register file, I don't know anymore if it is the complexity or the speed of a register file with the number of inputs output ports is of the order of the cube or something like this. So that is grows very fast, so you cannot do efficiently large register files with very many ports. And one solution is to have two register banks and two groups or clusters of functional units that are connected. A bit, if you want, as a sort of two VLIWs working in lockstep, right? So it's a classic architecture that other actually VLIW proponents have used at some point. HP was in the market with ST Microelectronics for embedded VLIWs. I'm not sure they still exist commercially, but they also have this possibility of creating clusters. The problem of this is that you need to split something, right? You need to decide essentially what goes in one set of functional units and what goes on the other set of functional units, right? It's part of the decision of choosing the functional unit now has an impact also on the cluster, essentially because the connection between the cluster is very low bandwidth, right? You see a little bit more the details here. There is a possibility for only one operand to be used in the other cluster, or here the same thing in the other direction. So there are exceptions and there is communication between the clusters, but this communication is extremely costly and extremely rare. So in many cases where you have partitioning in a computer architecture, if you do it, it's typically in cases where it is trivial to decide how to do the partitioning. For instance, you have caches and you have, for similar reasons, you have a cache for the data and a cache for the instructions. And why would you have two caches instead of one? Because you don't want to put on the same cache too many ports, right? But what is the difference there? Is that you know perfectly well when something is an instruction. If it has been called from the fetch unit, it's an instruction. If it has been called by load store units, is a piece of data. And so where to put in which of the D and I caches is a choice that is absolutely self-evident. A similar case where you have multiple registers and somehow some clustering of maybe a similar sort in a sense is when you have integer and floating point registers, which typically are not mixed up in the architectures, even if they are the same number of bits. These days, they are often of similar precisions, if not the same precision, but still they don't get in the same register file. Why? But because, again, I want to have register files that have the minimum number of ports and the minimum number of elements so that they are as fast and as small as possible. And again, I know exactly what goes into each. So in other cases, the split, where this split is successful, is self-evident. And here is not self-evident, right? What you need to do essentially here is that you need to have a way to do this partitioning and scheduling. And the partitioning is something that you sort of do before. And then from this partitioning, you do a schedule where the cost in time of a dependency, right? Here is a dependency. I let you read the slide maybe more in detail, but I think the intuition should be there without reading, is that if you have a dependency that is across the two partition, that is, my value has been produced in the other cluster, and now I need me functional unit in the second cluster, I need a value that comes from the other one, I have an additional cost in latency that is the cost of bringing here the value that I need. And so, as usual, we want to have the schedule that is the shortest, but now I have two phases, two things that I need to do: partitioning, deciding which nodes are executed on this, which operations are executed on cluster 1 and which operations are executed on cluster 2. But the cost of this partition will become clear only when I try to do some scheduling. So I have two problems that are intertwined, interspersed, and make the solution complex, because basically I want to solve both problems at the same time. So I have two problems, and again, the problem is that each of these problems is per se hard, NP-hard, and so if I put them together, any of the heuristics that I have for an individual of these two problems somehow gets screwed up. So again, and I don't want to spend more time on this problem, but somehow it's an old problem, because people have been looking in exactly this kind of context since the 80s at ways of doing this partitioning, but it's a very hard problem, and solutions exist that are not too terrible, but the computational cost is very, very high, and you lose a little bit sight of the intuitive complexity of the problem, or of the intuitive good solution of the problem. We arrived to the end of these 4 examples, and I hope these 4 examples help you get a sense on one side of what kind of weird use people expect to do of some of the functional units that we have introduced, or features that we have introduced in these DSPs, and on the other side give you a sense, maybe more important even, of how the irregularity might damage our compilation process. And this is an extremely important thing to get a sense of. It's not important to learn all the details, but if you will find tomorrow yourself with a basic processor and you'll ask yourself, what can I do to make this processor more efficient for a given set of applications, you need to be conscious of what impact you may bring on the ability of people to produce code for your processor once you have optimized it. And again, maybe as was mentioned in the 2 weeks previous to the last, it becomes more and more possible to do this. At some point, I think people were thinking computer architecture is finished. Basically, there is Intel that dominates the market. Maybe there is ARM that is coming as an emergent Intel in a different market, but that's it. And nobody does computer architecture. In fact, if you go back maybe 30 years or so, the European Union basically said, we give up. We don't give money to research in computer architecture because it's wasted. There is no point, right? I think it was a very narrow and myope view, but apart from that, things have changed dramatically, because now in system on chips, in embedded systems, there are actually a huge number of opportunities for doing your own processors, including FPGAs, of course, and maybe FPGAs in the cloud, where you may tune and create processors devoted to an application that you want to do. If you go and read, for instance, one of the papers on Catapult by Microsoft, I remember the fact, I'm not sure that it's in the paper, but I suppose it is. They did actually several designs for the different parts of the index building that they used Catapult, that motivate the development of Catapult. So for Bing, right? They used it for Bing, and some of the designs that they came up to for as pure accelerator were essentially some extremely dedicated classic processors, a large number of classic processors that were extremely dedicated again to the application. But they had the need to generate code automatically, to get from some high-level rules that were coming from the Bing team, code for these strange, absolutely awkward processors. And this is where these informations come to fruition, where this learning is important. You can do processors that are completely weird, but if you have to generate code for them, you better not screw up some of the things. And some of the things that you may screw up depend by this phase coupling. The fact that some of these decisions that any compiler has to do are not reasonably independent. They're never independent completely, but are reasonably independent. Instead of being reasonably independent, maybe they are hardly, they are strongly interconnected. And that is bad. That is bad because basic heuristics that you have cannot be applied anymore, and basically, ultimately, good solutions cannot come out automatically. So this is something to keep in mind whenever you will be thinking of doing a special dedicated processor.